Hi, this video we're going to be talking about what's typically called the normal curve. So what we're really doing is actually just building upon the empirical rule for bell-shaped data that we had looked at back at the end of chapter 3. And so again, bell-shaped, that means that we have that symmetric bell shape, the mean is right in the middle, and we know that approximately 68% of the data was within one standard deviation, approximately 95% of the data was within two standard deviations, which also gave us our boundaries for being unusual. Anything that happens less than 5% of the time is considered unusual, or if we're talking about a probability distribution, anything outside two standard deviations of the mean would also be considered unusual. We also had this picture, which again, I think helped to kind of illustrate what's going on. And essentially what we're going to be doing, again, is trying to go a little bit more in depth and talk about what's going on. What do these percentages and probabilities really mean if it's not just, one standard deviation away? What if it's some other non-standard distance from our mean? And this is where the normal curve comes into play. So it's sometimes called the normal distribution curve. It's sometimes called the Gaussian distribution. But essentially what we're looking at is any probability distribution that has this normal or symmetric bell shape. What we're going to be able to do is actually equate the area under the curve to a probability. And again, anytime we have this bell shape, we're just going to call it a normal curve. And again, it's the one that shows up most frequently. It's fairly standard. And what we're going to be tying this into, especially when we get to our later chapters, like chapters 9 and 10, we want to take different types of distributions and make sure that they can fit this normal curve so that we can run our statistical analysis. And one of the last things we looked at in chapter 6 was that when we had our binomial probability distributions, so again, it's a probability distribution, we know that if we fit that little equation there at the bottom, that the sample size n times the probability for success times the probability for failure is bigger than or equal to 10, my data is going to end up bell-shaped, which means I'm actually going to be able to apply my normal curve information about that particular distribution. So again, it might sound a little confusing at first. When we get to some examples in just a minute or two, hopefully it'll become a little bit easier. But before we do some examples, I just want to go over some properties of this normal distribution curve. First of all, again, it's symmetric. It's that bell-shaped, and the center is always going to be the mean. And remember, we use that variable mu, that Greek letter mu, to denote our mean. Again, that's always going to be the center of our data, and it's going to be the peak of our data. Anyway, when we have data like this, the mean, the median, the mode are all equal to each other. It's going to be that tallest peak of my curve, and again, that tallest peak is going to be my mean. It has inflection points at points that are one standard deviation away from the mean. Now again, that's not all that important for our purposes here in Stats 1. If you were taking a higher level statistics course where what we actually do is we involve calculus quite a bit, then inflection points are a little bit more important. For your purposes, it's just sufficient to just kind of mention them and move on. Next, the area under the curve is 1. And again, this goes back to my probability distribution has got to account for every single possibility, which remember, when we sum our probability distributions, we have to end up with 1. It's got to account for all of the data. So the area under the curve is 1, and then we're going to be able to kind of divide and split up the area under the curve depending on our particular needs. Now, if we put some of these things together, the area under the curve is 1. Everything is symmetric about that mean. That means the area to the left of the mean is a half, and the area to the right of the mean is a half. It has to be symmetric. And again, we're going to use some of that to kind of logic our way through some of these more complicated probability problems that you'll have to set up for your homework. And lastly, as my values along that x-axis increase without bound, meaning they get larger and larger either to the left or to the right, my probabilities are going to approach 0. basically my curve gets really, really close to the axis, which means that the area under that curve, there's, well, no room, there's no area. It goes to 0. Now, it can never be below 0 because you can never have something with a negative probability. Remember, probabilities have to be between 0 and 1. But we are going to have to take that into account, that this curve is going infinitely to the left and to the right when I draw it. Now, before we actually see that in practice, just a few things that, again, I want to mention about the shapes here. With the shapes, again, the mean is going to shift where the peak is. If my mean is at 0, the peak is at 0, as with this first example, right? My mean is at 0, so my peak is at 0. With the second example, my peak here is at 3, and my mean is at 3. So again, the mean is always going to be that peak. But because they have the same standard deviation, remember, standard deviation is our measure of dispersion. It's our measure of spread. It tells us how spread out the data is. Well, if the standard deviations are the same, that data is going to be spread out in the exact same way. And we can kind of see that we just shifted that normal curve to whatever is appropriate for our particular mean. Now, however, if I did adjust the standard deviation, remember, again, like I said, standard deviation has to do with the shape and the dispersion. And if I have a bigger standard deviation, that means the data is more dispersed. That means it'll be spread out over a further area. And so in this case, we see that the blue curve has a standard deviation of 2, and clearly it's, well, it's more spread out. Whereas with the pink one, our standard deviation is 1, and so all the data is going to be much more narrow, much more closer to that mean. There's not going to be as much spread. Now, a lot of times we use the standard normal curve. And again, this is really convenient. This was more convenient back before we had tons and tons of technology, but it's still convenient now as well. And we define the standard normal curve to be that bell-shaped with the mean at 0. So again, it's centered right at 0. So it's centered at my number line, which means, again, half of the data is going to be less than 0, and half of the data will be bigger than 0. So half the data will be negative, half of it will be positive. And then the standard deviation is just 1, which again is just a very convenient notation. Because what we're going to do is go back to this concept of z-scores. And remember, the formula for the z-score was my data value, x, minus my mean, mu, and then divide that by the standard deviation. But if my mean is 0, x minus 0 is just x. That doesn't do anything. And if I divide by 1, that doesn't do anything. And so my z-score and my x-score are basically the same exact thing. And so you're going to see that, again, as you go through your homework, they're going to interchange x's and z's, which is fine because they're basically the same thing. But again, don't get too confused if they've set it up with x's, but I'm doing my examples in terms of z's. It's the same exact process. And again, just going back to how we interpret what's going on here. The area under the curve is equal to my probability. And we're going to have to create bounds here. Now, this is one of the things that I had mentioned a little bit earlier. This curve goes out to negative infinity. That means this curve keeps going out, even though we didn't draw it, it's going to keep going out all the way, well, infinitely. It'll extend past the left end of your screen, all the way around the entire universe. And on the right side, it's the same idea. It's extending all the way to infinity. But we don't really have to sketch it because, again, once I get down to really, really far out, for example, this spot right here, there's not much area. There's not much going on there. It's practically 0. And adding up a bunch of zeros isn't really going to make a difference. Now, regardless of the context of the problem, we are going to have to consider it going from, well, negative infinity or positive infinity, depending on, again, the situation. But, well, we'll talk about how to actually write that in your calculator in just a second. Because first we have to know, well, what am I actually using my calculator for? So we're still looking at distributions, just like we were with Chapter 6. Chapter 6 was that binomial probability distribution. Now we're looking at the normal distribution. So we're going to find our calculator function under the same exact spot under distributions. And again, typically you find it by pressing second and then the vars button. And then just scroll through till you find the normal CDF. We are not going to be using the PDF function at all. With the normal curve, again, we're looking at ranges of values. So we're going to be using the normal CDF, and this one needs 4 values. And again, whether you have the stats wizard or not, they're going to go in this order. The lower bound of the data, the upper bound of the data, and then the mean and the standard deviation. But again, that normal curve, when I talk about the lower bound and the upper bound, if there's no point where the shading stops, if it goes infinitely, that shading is unbounded, and so you're supposed to use negative infinity or infinity. Now again, your calculator actually can't go all the way to infinity because, well, actually infinity is not really a number. It's just this concept that it keeps getting bigger and bigger and bigger, that you can always come up with some number bigger than it. So what we're going to have to do to kind of get around that is that, again, regardless of the context of the problem, you're just going to have to type just a huge, huge, huge number instead of infinity. But let's take a look at some examples. Find the area under the standard normal curve that lies to the left of z equals 0.96. So again, my biggest suggestion that I could possibly make with this entire unit, and it's going to help you as we do the next units too, because this normal curve is a critical part of everything that we do in our third unit when we get to inferential statistics. And so my advice is to make sure you sketch. It doesn't have to be the prettiest sketch in the world. A quick normal curve. Always put your mean or mu in the center, right? And then just, again, draw a rough picture of what it is you're trying to look at. So again, we went to the left of z equals negative 9.6. Remember, 0 is at the middle, so negatives go to the left. And I went to the left there, so I want that whole area. That's what I shaded. So my lower bound, like I said, this is actually going all the way out to negative infinity, but I can't type in negative infinity. So I just need to type in a very small number, but a big small number, if it makes sense. Something like negative 1,000,000. And honestly, it doesn't matter. Throw a bunch of zeros at the end. That's not all that important. The upper bound, again, that's where this gets cut off at the right-hand side. And so it's getting cut off at the right here at my z-score. So that's my negative 0.96. And again, because it's a standard normal curve, the standard normal curve is always going to have those two values, 0 for mu and 1 for the standard deviation. And once you have all those values, it's just a matter of plugging them into the function, or if you have the wizard, pasting into the function, hitting enter, and then that gives you the area, which is also equal to the probability. And so again, that's the probability that your data is going to have a z-score of less than negative 9.6. So again, we're still dealing with inequalities and understanding what inequalities look like, just like we were with Chapter 6. And it's just that, well, again, now I'm looking at z-scores. But like I did say earlier, don't be too surprised if when you're doing your homework, your book just switches it up to x, right? X is less than negative 9.6, because again, those variables are fairly interchangeable when you're doing that standard normal curve. Next example, find the area under the standard normal curve that lies to the right of z equals 1.72. Now again, we have a positive value, which means it's definitely to the right of my mean. And like I said, it's a good idea. Go ahead, always draw that mean in and what it is, in this case 0, just because it'll help you to, well, basically assure you're not making any mistakes later on. So in this case, again, it's to the right. So again, shade to the right, which I already did with the blue. So my lower bound, remember, lower is left. So where does this start on the left-hand side? Well, that's my z-score, 1.72. My upper bound, well, again, this is going to infinity, so I need a really, really big number. And I just typed a bunch of 9s this time. It doesn't exactly matter what it is that you type. Your book is going to suggest that you use 1 and then scientific notation, which is that e to the 99, which is literally the biggest number your calculator can handle. And that's totally appropriate too. That's a 1 with 99 zeros at the end of it. That is huge. That would work. But you're going to notice that if you just pick a big enough number, the difference is basically negligible because, like I said, you're just at some point just adding up a bunch of zeros. We still have our standard 0 for the mean, a 1 for the standard deviation. And again, my probability I'm looking at. And again, this is the same thing as the area. That area to the right is the same as my probability. And again, just a matter of plugging everything in, hitting enter, and we see that that probability is 0.042716. So about a 4% chance of ending up that far away from the mean. Okay, on to example 3. So in this example, we're still dealing with the standard normal curve, but now we're going to look for the area or the probability between two z-scores. So now we have a bounded region under our normal curve. Again, always a good idea to make sure you start with the mean being that peak. And again, in this case, it's 0. And then since we're bounded here between negative 1.02, which would be obviously to the left because it's negative, and 0.63 to the right, which is obviously positive, those just become our bounds. No need to go to infinity or pick a big number. We have our bounds given right there. We still have our standard setup with our mean being 0 and our standard deviation being 1. And again, what we're trying to see is that region between those two values. And you see here we're looking at the probability of a compound inequality. What are the z's between negative 1.02 and 0.63? And again, you're just going to type that into your calculator, press enter, get your answer, and it looks like this answer is 0.5817885, and that's it. And again, those are really the three types of finding probabilities and finding areas that we're going to deal with, either unbounded to the left where it's smaller than, unbounded to the right where it's bigger than, and then here in example 3, when we're actually bounded in the middle between two values. I do want to warn you that my stat lab is going to recommend that you do all of this work by looking up tables in the appendix of your book, and that is completely unnecessary. Use technology here. It's perfectly valid to go through and try to look up the values in the book and write things down, but your calculator has that entire table stored inside of it. Use the technology to make your life easier. There's no need to look up tables if a calculator or a computer can do it for you. Your job is going to be to interpret those answers, which, again, in the context of this problem, what this is saying is that the probability that you were within 1.02 standard deviations of the mean and 0.63 standard deviations of the mean, if you are in that range between there, the probability of being in that range with your z-score is that 0.5817, which again, you could move it over 2 places, so the 58%. All right, there's a 58% chance you'll be between those two. So again, just use technology and you should be all right. Now, the nice part is, again, all of this works together. How far away we are from the mean, that z-score, and the areas and the probabilities, they're all related to each other. So we can work in the opposite direction as well. And again, I highly recommend that you use technology instead of the tables to do this. And what we're going to do is, well, again, it's under distributions. This time it's called the inverse norm, right? Inverse meaning we're kind of working in the opposite direction. We're kind of working backwards. And so the way the inverse norm function works is that it's going to ask you for the first value is the area, then a comma, and then your mean, and then your standard deviation. Now, when it asks for the area, it is the area or the probability that is to the left of that z-score. All right, the area or the probability that's to the left of the z-score. It always goes in that cumulative fashion, right? Just like our binomial probability distribution went cumulatively, right? It added everything up. the inverse norm function works the same way. So again, you might have to draw that picture first and do a little bit of algebra and logic out. Well, okay, what is it actually going to be to the left? But again, typically it's not too bad. So let's take a look at an example. What if I want to find the z-score that separates the middle 30% of the data from the tails on a standard normal distribution? So we're looking for the z-scores that, well, separates that middle. So there's actually going to be two of them. There's going to be the first one here on the left, and then the second one here on the right. There's going to be two different z-scores. But again, the idea is that when I use the inverse norm function, it's going to have to add up from left to right. So I'm going to have to figure out, well, how do I set up the area now that is going from the left to the right? The 30% is not going to appear in what I actually type into the calculator. Well, the nice part is we can logic this out. If the middle is 30%, then the tails have to be 70% by the complement rule. Again, we have to add up to the entire thing. It's got to add up to 100% or add up to the number 1. Which means, again, if we have the middle 30%, then there's 70% in the tails. And I also know that this distribution is symmetrical, which means the tails have to be equal to each other. Which means if there's 70% in the tails, half of it is in the left tail, or 35%, and half of it is in the right tail, again, 35%. And again, just a real quick sketch trying to set up where all these areas are located. And again, taking that extra 5 seconds to sketch out a normal curve is going to make such a difference in your ability to do this accurately that please don't skip steps and don't try to just do it in your head. You're going to make mistakes. But let's actually finish this problem. So the first z-score, that left-hand side, the area to the left is, well, the 35%, except I do need to write that as 0.35. Again, we always have to convert our percents to our decimals. So when I plug this in, well, the area is 0.35, my mean is 0, my standard deviation is 1, plug it all in. My z-score is negative 0.38532. Now, this should hopefully make sense. My first z-score is to the left of the mean, right? And my mean is 0. So if I'm to the left, I'm definitely going to have a negative value for my z-score. Now for the second one, we're now to the right, which means my z-score to the right better be positive. But we're going to have to do a little bit of logic here as well, because it has to add up from the left to the right. So in this case, for my second z-score, the area is, well, I add up that first 35%, then I have to add up that next 30%, and so the area to the left, 35 plus 30 is, well, 65%, and of course, convert that to 0.65. And then it's just a matter of plugging it in. And we plug it in, the 0.65, then the 0 and the 1, and I get 0.38532. Now, notice, when I look at those two values, are they similar? Well, of course they are, right? I'm splitting up that middle 30%, and I know that my curve is symmetric. That means my z-scores need to be symmetric as well. I should get one negative for the left and one positive one for the right. And I hopefully that makes sense when we look at this picture and we understand how we're actually breaking down this curve. Now, of course, the main power of this is we don't have to use the standard normal curve. That's where technology has made life so much better and has actually made statistics approachable to, well, almost anyone. You know, before, you used to need to know advanced calculus to be able to do things like this. Oh my God, the TA83 and the TA84 have made life so much easier and so much more convenient that we can do all kinds of statistical analysis and let the technology do all of these complicated computations for us. So for this example, and we're going to actually look at a few regarding the same scenario, the lengths of pregnancies are normally distributed with a mean of 268 days, just about 9 months, and a standard deviation of 15 days. So what is the probability of a pregnancy lasting between 260 and 272 days? Well, as always, sketch the picture first. Sketch the picture first. Always, always, always. Remember, your mean is always the one in the middle. So that 268 goes right in the middle. And again, I'm looking between 260 and 272. So again, it doesn't have to be exact, but mark roughly where those would be on the number line. And then it's just a matter of, well, using that normal CDF function again. My lower bound now is 260. My upper bound is 272. And this is the genius part about using your calculator. We can just now adjust and type in that mu was 268 and sigma was 15, and it's going to do all the z-score conversions for us. And then just type that right into your function or have it paste, and well, there's your answer. 0.3082. So about 30% of pregnancies, or about 30.8% of pregnancies, last between 260 and 272 days. Part B. A baby is considered premature if they're born at least 30 days early. So what proportion of babies are born prematurely? Well, again, always, always, always sketch that normal curve. Mu is always the first part. And if I'm at 30 days earlier, with 30 days earlier than average is, well, 238. I just subtracted 30. I know that anything earlier than that also counts. So again, I'm shading over here. Now, this is where you want to be very, very careful. And this is where I see a ton of mistakes. Because now that we're doing this in the context of a pregnancy, right, I need my lower bound and my upper bound. Well, we know that it doesn't make sense that a pregnancy could last for negative infinity days because you're not giving birth before you were ever pregnant. That makes no sense in context. However, with the normal curve, it's not about what works in context. We have to, well, basically follow the math of the normal curve. So my lower bound is some really, really small number, negative 10 million in this case. And again, obviously a pregnancy can't last negative 10 million days, but that's what we have to use. This right here is almost always where we end up with issues. But then my upper bound is the 238. My mu, we know the mu. The standard deviation didn't change, so that's still 15. Plug it in, let the calculator do its work, and we get that probability, or the proportion, is 0.02275. So again, a little more than 2.25% of pregnancies end up premature. And here's the last part, which is really, really convenient with the technology as well. Let's say a doctor decides to induce labor if the length of the pregnancy is in the top 10% of all pregnancy lengths. That means that if you're pregnant and you still haven't had the baby by your due date, and it's, well, getting far past your due date, the doctors can induce labor. They can basically try to artificially get labor to begin so that you can birth the baby using, well, any number of methods. So this doctor says that if you're in the top 10%, he's going to induce labor. So at what length would the doctor induce labor? Now, the thing here is to recognize that that 10%, that is my probability. All right? The top 10%, I'm now given the probability, which means what I want to find would be my z-score. And the calculator is going to be able to scale my z-score for me, which means what we actually want to use in this case is going to be the inverse norm function. So remember, the inverse norm function is always area to the left. So even though I want the top 10%, I'm going to have to think of it as going from left to right, which is the 90% of the data, which again we have to convert to 0.9. The mu is the same, the standard deviation is the same, and then it's just a matter of, well, basically plugging it in. And then the calculator is going to spit out 287.22, which again would mean that what we've really found is this data point right here was 287.2. And that is going to be the number of days that a doctor would wait before inducing labor. And again, given the context of the problem, well, we probably wouldn't do a part of a day. You'd have to round that to whatever's reasonable given the particular problem. All right, so I hope that helps with explaining what the normal curve is and particularly how to use it. Take some time to review this material because I know we're finishing up that second unit now with talking about probabilities. This is something you cannot forget after our exam. We are going to be using the normal curve for the remainder of our course, and it's going to show up quite frequently again. So really, really make sure you spent some time to really make sure you understand this particular section. So good luck studying, good luck with your homework, and as always, please email me if you have any questions.